We're going to talk about what relative atomic mass is, how it is determined, and why we say relative atomic mass is based on carbon-12. Mass and moles have been covered in a separate video. Check the links in the description below. Relative atomic mass has a rather complicated history. Early chemists couldn't measure the masses of different elements based on atoms, as they are simply too small, and many scientists didn't even know atoms existed. Instead, to try and get around this, rather than compare a specific amount of different elements to a known standard, such as a gram, they simply compared them to each other. This sometimes worked well, and early editions of the periodic table were based on those relative masses. However, it was always tricky to know exactly how much of each element there was when making comparisons of mass, and this did lead to some errors. For any comparison between elements to make any sense, one element has to be chosen as a standard to compare all the other elements to. The question is, what element should be used as a standard? Initially, hydrogen was used. Hydrogen has the lowest mass compared to all the other elements, meaning the masses of other elements must be multiples of hydrogen's mass. Because of this, it was assigned what's called a relative atomic mass of 1, and all other elements' masses were based on this. An element that has 3 times the mass of hydrogen would have a relative mass of 3. An element that has 4 times the mass of hydrogen would have a relative mass of 4, etc. Things got a bit more advanced when new instruments were developed in the early 20th century. In particular, something called the mass spectrometer. These instruments allowed, for the first time, atoms of different elements to be assigned accurate masses relative to each other. We could now study individual atoms. The only problem was all this equipment made everything much more accurate, and things called isotopes were discovered, and this meant a more stable standard was needed than hydrogen. Samples of hydrogen were found to contain hydrogen atoms with different masses, isotopes, and this made accurate comparisons of mass between elements based on hydrogen quite difficult. A bit like having a bunch of rulers all labelled as 1 metre, but they aren't all exactly 1 metre. How would you know which one is the right one to use to measure other things with? To get around this problem, it was decided in the 1960s that carbon-12 should be used as the standard for relative atomic mass. Carbon-12 is a naturally occurring isotope of carbon that is very stable and common, making it easy to get hold of and store. This now meant that you could be much more certain about the purity of the sample you're using for relative atomic mass comparisons. As a result, relative atomic masses of elements are now described as the weighted average of one atom of each element compared to 1/12 the mass of an atom of carbon-12. This sounds really confusing. Let's break it down. From experiments and mass spectrometry, we know that an atom of hydrogen, the smallest atom possible in the universe, has 12 times less mass than an atom of carbon-12. This means all elements' relative atomic masses can be compared to this smallest possible relative mass. As a result, we describe relative atomic masses as being compared to 1/12 the mass of an atom of carbon-12, as this is the same as the smallest possible relative atomic mass. This smallest possible unit is sometimes described as an atomic mass unit, 1 AMU, or 1 unified atomic mass unit, U. We describe relative atomic masses as weighted averages, as we have to account for naturally occurring isotopes of elements. Within a sample of an element, some atoms will have different masses to each other. This means the average relative atomic mass of all atoms in the sample won't end up being a whole number. This is what made that problem with hydrogen earlier on when we were talking about a standard to use. The percentage of naturally occurring isotopes of an element should always be the same, meaning regardless of how much sample you have, the weighted average of all isotopes should be the same. For example, a sample of chlorine will always contain atoms of two isotopes, chlorine-35 and chlorine-37. The amount of chlorine-35 isotope in the sample will be 75%, and the amount of chlorine-37 isotope in the sample will be 25%. These are sometimes referred to as percentage abundances. The average relative atomic mass of all the chlorine atoms then will be 35.5. Another way of thinking of this is that for every 100 chlorine atoms in a sample, 75 of them will be the 35 isotope and 25 of them will be the 37 isotope. To find the average mass of one atom then, you can find the total masses of all the atoms present, 75 times 35 plus 25 times 37, and then divide by the total number of all atoms, 100. This gives you a weighted average of 35.5. It's weighted because we have taken both of the different isotopes into account and their percentage abundances. So, to summarize, relative atomic mass is the weighted average mass of one atom of each element compared to 1/12 the mass of one atom of carbon-12. Atoms of elements are too small to compare to grams for sensible use, meaning their masses are instead compared to each other. Carbon-12 is chosen as the standard as it's a stable isotope that is easy to obtain and store. The smallest possible atom from the element hydrogen has a mass that is 12 times smaller than an atom of carbon-12. This means the atomic masses of all elements can be considered as being relative to this smallest possible mass, which is actually 1/12 of the mass of an atom of carbon-12. Relative atomic masses are described as weighted averages as there are natural isotopes of elements, meaning the average relative masses of atoms of an element in a sample won't ever be a whole number. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.